All right, so let's take a look briefly at molecular orbital theory. Now, this is not going to be on the exam, but we do need to keep moving forward. We've got a lot of stuff to cover this semester. So I keep mentioning that our VSEPR theory and our valence bond theory work really well when we're talking about organic molecules, especially things that have to follow the octet rule, but they're not so great when you're dealing with inorganic compounds. So I don't really love the idea of an sp3d hybrid orbital. As an inorganic chemist, we would be thinking about that in a different way. So we're going to look at another kind of theory that explains bonding. But before we get into that, we're going to look at what have we said so far, what works well, what doesn't work well. So far we've talked about VSEPR and Lewis dot structures. We kind of put those two together. VSEPR theory says our electron pairs are going to spread out as much as possible. But the problem we ran into was that we couldn't explain our bond angles with VSEPR theory if we were using atomic orbitals, because VSEPR said we're going to have an angle of 120, we're going to have an angle of 109, but our atomic orbitals, especially the p orbitals, were all at 90 degrees from one another. So we added a layer with valence bond theory. And valence bond theory said, okay, we're going to take the atomic orbitals, we're going to mix them all together and form these hybrid orbitals, and those orbitals can point in different directions. So this does a really great job of explaining how those bond angles occur. And so it works really well when we're dealing with things that follow the octet rule, but it does have a few problems. Now, those problems are minor for most things, but we're going to remember that for a model, there's always going to be some problems. It can still be useful for helping us to understand something, even if there are problems. So what are the problems? They don't explain paramagnetism. So paramagnetism means we have unpaired electrons. And in all of our Lewis structures, we try to pair up the electrons. They're either paired in the lone pair or they're paired in the bond. We don't like the free radicals. We can't follow the octet rule with a free radical, and we know that they're unstable. But there are a handful of molecules like oxygen that are stable. So the models we currently have don't answer the question, why are there some stable molecules like oxygen that are paramagnetic? Okay. So when we draw the dot structure, we see the double bond. We see that it is that everything is paired up. We have bonds and we have lone pairs, so we wouldn't guess that it was paramagnetic. Now, when we check the distance between the atoms, that lines up pretty well with how big the distance should be. But otherwise, it doesn't explain the paramagnetism. Oops, what did I just do? Okay. The next problem we have is that the VSEPR theory and Lewis structures predict the electrons will be localized. Especially with Lewis dots, we say, okay, the electrons are either attached to one atom in a lone pair or they're in a bond between two. And when we try to explain resonance or delocalization, we run into the problem of, well, we don't actually have one structure or the other, it's kind of in between. And we can't really put the dots on if we have bonds that are in between. So we can't get an octet and show in between bonds. So that's a little inconvenient there. And then one other problem with these models that I didn't put on here is that you might ask the question, well, how does an atom know what kind of hybrid orbitals it needs to form before it makes a new molecule? And, you know, atoms not being sentient beings, it doesn't make a lot of sense that they would know ahead of time what they were going to do. Okay, so we're going to start on a new theory called molecular orbital theory. So molecular orbital theory helps to explain these things. I like it because we don't have to run into these problems that are there, and it works for the whole periodic table, not just the upper corner there. So I can use it for my transition metals. I can use it for my, my inorganic sulfur hexafluoride, and I can use it for organic molecules. So it's nice that it works for everything. The problem is it's complicated. And so since it's complicated, we're just going to take a one baby step today, and we'll get more into it on Monday. Okay, so the idea of molecular orbital theory is that we have atomic orbitals on atoms. So if you think of hydrogen, there's a sphere, that's the s orbital. So if I have two hydrogens, those two different nuclei are going to each have an s orbital. And as those atoms come close together, those orbitals are going to overlap. Now, so far, this sounds a lot like our valence bond theory. You have overlapping orbitals. Valence bond says they're just overlapping. They're still attached to one atom. They're still hybrid or atomic orbitals. Molecular orbital theory says once they overlap, they're going to make some new orbitals. Okay, so molecular orbitals are going to come in two flavors. And when we make our orbitals, we're going to follow that same rule. However many orbitals we started with, that's how many we end up with. So we said hybrid orbitals was equal to atomic orbitals. We're going to say molecular orbitals are equal to atomic orbitals. So we're going to have the same number. So that means if I have two atomic orbitals, I'm going to form two molecular orbitals. And the way we do this, there's a lot of higher level math involved. We're not going to do the math part of this. So each orbital has a wave function, it has some expression that says this is where the orbital is. And so we can say, okay, expression for the first orbital plus expression for the second one. So we can add those together, or we can say expression for the first orbital minus the expression for the other. So we can subtract them. Now we're just going to think about this graphically rather than mathematically. But basically what we're saying, we're just going to deal with hydrogen today. We have hydrogen A and B, each has a 1s orbital. So I can say 1sa plus 1sb, or I can say 1sa minus 1sb. When we add them together, we're going to get a bonding orbital. When we subtract them, we're going to get an anti-bonding orbital. I'm going to do one more slide real quick just so we can see what this looks like. We have two isolated atoms. When they get together, they're going to overlap together, forming this kind of oblong orbital. And that's going to be a bonding orbital. When we subtract them, the space in between them becomes a node. That's not allowed. We'll explain why on Monday. But this is what we call an anti-bonding orbital. Okay, so those are going to be our molecular orbitals, and then we'll see what we're going to do with those on Monday. Again, you don't have to worry about molecular orbitals for the test. It would be a good idea to look at that last section of chapter 8 before Monday then. All right. I don't see any further questions. If you have them, you can put them in the chat box, but otherwise we are done for the day. I have lab tomorrow afternoon, but I will check my email today and tomorrow if you have questions. So I can't meet with you tomorrow afternoon, but I can email.